Assalamu alaikum everyone and welcome to today's conference which will be about zero-shot reinforcement learning to be hosted by our ex-leader Nazim Bendib and AI Summit 26. Nazim, it's always a pleasure to have you with us, and yeah, the stage is yours.
Thank you. يعطيكم الصحة. السلام عليكم. إن شاء الله تكونوا بخير. Thank you for inviting me. My name is Nazim Bendib. I was an ex-president of School of AI Algiers. And today I'm going to talk a little bit about reinforcement learning in general, but more specifically about zero-shot reinforcement learning. All right. Okay, in AI we have like a lot of fields. Mainly, we see supervised learning and supervised learning, and we have also reinforcement learning, which is a little bit different, but we use basically the same techniques. We have neural networks that we try to train, etc. And well, we can skip this. In this presentation, it's going to be a little bit advanced. So, as prerequisites, you should know what are states, actions, rewards, transition dynamics. We can get over this quickly. So in reinforcement learning, the goal is to train an agent, so c'est un agent that we need to train it. And this agent acts within an environment. So for example, you have a robot and the environment is like, I don't know, a room. And the robot needs to clean the room, all right? So we train it to do this task. And if it does something in the context of cleaning the room, for example, I don't know, lifting some toys, putting them on the table, etc., we give it a positive reward. So we reward the agent, and the agent is going to understand that this is a positive action. I need to do this more often. And if the agent like does some nonsense action, we are going to penalize it so that the agent understands that that action was bad and it should not do it again. So a state is like the actual state of the environment. The action are the actions that are done by the agent, for example, picking stuff, throwing stuff, etc. The reward is what we give it as a response to its actions. So generally, it's a scalar, c'est un scalaire. It's either positive, generally, when the action is good, and negative when the action is bad. And the transition dynamics is what represents the environment. So for example, if the agent picks a ball and throws it, this ball is going to follow the dynamics of the environment. So it's going to follow a certain trajectory, etc. And okay, so we train the agent to have a good policy. So what is a policy? Generally, we refer to it as P. And the policy is the strategy of the agent, okay? So a good policy is a policy that gives us a lot of positive reward. In contrast, a bad policy is a policy that gives us a lot of bad rewards. And the goal is to have as much rewards as possible. So the goal is to have like an optimal policy that maximizes the reward. We have the Q function, so Q de SA. So Q function is called the critic, and it's a way to evaluate how good a state is. So Q is going to take S and A, so S for state and A for action, and it's going to return a scalar, and the scalar is going to be like very high if that state and action are promising, and it's going to be low otherwise. A value function is very, very related to the Q function. So a value function only takes S, and it's going to evaluate the state to know whether that state is very promising and like it has a lot of potential to gain a lot of rewards afterwards or not. Basically, it's the expected discounted return. And for the rest, like to do all this, we need to understand some some basic linear algebra. So for example, what is a vector, what are dot products, matrix, etc. And I think you got this. Okay, so what's the problem that we're trying to solve? In typical reinforcement learning problem, we have the environment, which is an MDP, Markov decision process. And we have an agent that is acting within this environment. And the goal of the agent is to maximize a reward. So in the typical error problem, we have what we call a reward function, which is a function that takes the current state generally and is going to return how good is that state. So it's like a function that the user designs, and the agent is going to be trained with respect to this reward function. And then, as we said earlier, the goal of the agent is to maximize the reward function, and so it needs to acquire a really good policy. Okay, right. So this works very well when we have like one predefined reward function, but the problem is that what happens if we change the reward function? So if we change the reward function, the problem is that we are going to need to retrain the agents from scratch, because when we train it for a certain task, it's going to get very specialized in that. And so when we change the reward function, we need to train it again. And that's like very annoying problem, because training takes a lot of time, takes a lot of compute. And so training again is like a whole waste of compute and time. All right, so for example, in robot navigation, if we train one robot to go to room A, and now we want it to go to room B, we will need to train it all over again. Same thing for games, etc. So the idea is that we need to train a general agent that is not very related to a specific reward function. So in some way, we need to separate what the agent can do from what that reward function is really specialized in. So yeah, to separate this, we can use what we call a reward decomposition. So we are going to assume that the reward function that we are going to solve is a linear combination of state features. So S is the state, phi of S is the state features, and we are going to assume that the reward function is a linear combination of the state features. So basically, we are going to assume that the reward function is equal to the state features multiplied by a certain vector. So since it's like an affine multiplication, it means that the R of S is linear with respect to phi of S. Okay, and you can see that the reward function here is parametric. So it's R of W, okay? And this W is the same that we multiply by state features. So for example, if we put here W1, it's going to give us R of W1. And once we change the W, we are going to directly compute a new reward. So phi of S stays the same, but what changed is the vector that we multiply with it. Okay, so phi of S is the feature vector, and basically it describes what the agent sees. So for example, if the state is the current characteristics of the room, then for example, phi of S is going to be the position of the robots or the objects nearby, etc. W is just a weight vector, and it can represent like the preference of the task that we want to do. We can also call it a task vector. And yeah, it's going to be a vector. We have numbers in it. And by changing those numbers, we are going to change the preferences. And thus, we are going to change the reward that we want to solve. And by doing like the dot product, we are going to define a scalar reward. So typically, phi of S is going to have the same dimension as W. And for each dimension of phi of S, it's going to represent a certain characteristic of the state. And if we take like the W vector, the task vector, each corresponding dimension is going to represent the importance of that characteristic. Okay? For example, in phi of S, if, for example, we have like the fifth dimension that represents how many objects do we have, like did we collect? And in W, in the fifth dimension of the task vector, we have like a high scalar in there. It means that this reward function is going to favor collecting as many objects as possible. If we inverse that, if we put like a very low value for the fifth dimension, it means that this reward function favors not having any objects in our collection. And so again, by varying the task vectors while keeping phi of S the same, we are going to be able to vary the reward functions. And this is the essence of zero-shot reinforcement learning. So building on top of this, there is a notion of what we call successor representations. It's actually very old, but it's became to be like really useful nowadays to do like zero-shot reinforcement learning. So successor representation is like some sort of a measure. We refer to it as M, and it's going to take S and S prime, so it's two states, and it's going to quantify what are the chances of stumbling across S prime if we start from state S. Okay, so it's going to answer the question: if I start in state S, how often will I visit state S prime in the future? And so it's an expectation of the like discounted sums of the visitations. And this is like very similar to value functions and Q functions, so to the value and critic. It's exactly the same thing, except that we're going to multiply the discounted factors by 1 if we visit that state and by 0 otherwise. All right, so this like quantity, let me just enable this. So this quantity is going to be equal to 1 when the agent is in state S prime at time t, otherwise it's going to be 0. And all right, so this is going to be like a matrix. So for each S and for each S prime, you are going to have certain value, and it's going to represent like a visitation matrix by the end. What's very interesting about this is that once we train the successor representation, we can directly infer the value function of certain states by just doing like a dot product. So the value of S is going to be equal to the successor representation of S with respect to all S primes, to all other states, multiplied by the value of these states, by the reward of these states. So it's just like a dot product. And as you can see, this successor representation is independent of any task. So it's only dependent on the dynamics of the environment, but it does not care about the task that we try to solve. And this is what's interesting, because we can take the successor representation. It's just enough to multiply it with a certain R that represents a reward function, and you are going to infer in zero shot the value function with respect to the states. So in standard reinforcement learning, the policy P encodes the reward implicitly because we train it using a critic, and the critic is trained using one specific reward function. And if we change the reward, we need to do a full training. Whereas with successor representations, the successor representation of state S and S prime, it only encodes the dynamics of the environment, and it does not care about the reward function. Once we have the reward function in hand, we can just directly compute the value. And by directly computing the value, we can train the corresponding policy. So yeah, in standard RL, nothing is reusable. We need to train the whole thing, and it's very slow because we do this for every single task. Whereas with successor representations, the M that we train is fully reusable across tasks because it's only dependent on environment, and a new task is solved by doing one matrix multiplication. On top of this, we build what we call successor features. And this is like one step on top of this. So in successor representations, the question that we are trying to ask is, how often are we going to encounter state S prime? But in successor features, the goal is to predict the states that we are going to encounter. So here we need to pass S and S prime. We are just going to calculate this with respect to S prime, but with successor features, it's different. We only give S, and we say that if we follow a certain policy P, what is the discounted sum of the state features that I'm going to encounter later on? So the successor features are even richer than successor representations. And as you can see, they are also independent of the reward function that we are trying to solve. So it only encodes the dynamics of the environment. So phi of S is the feature vector of states S, as we explained earlier. And psi of S is a vector of the same dimension as phi. So as you can see here, it's just a discounted sum of feature vectors. So itself, it's going to be of the same dimension. And it's going to accumulate the expected discounted feature visits, not state visits. So exactly, it's going to predict what are the features that we are going to end up with by the end. And exactly like successor representations, if we want to calculate the value of state S, it's just enough to multiply the successor features with the task vector itself. And we do this because of this assumption that we made earlier that the reward can be decomposed, right? And so, and when we train the critic, generally, what we do is that we are going to try to predict the discounted sum of future rewards. But so it's basically the discounted sum of this term in here. But with with successor features, we are going to try to predict the discounted sum of state features. So it's going to be the discounted sum of this quantity in here. And so if we multiply all of that by W, since it's cumulative, then multiplying C of S by W is going to recover the critic or the value for us. So we get this value recovery. Okay, so as we said earlier, C of S only depends on the policy P, and it does not care about the reward function. It also depends on the environment because the policy acts within the environment dynamics, and it is task independent. The task weight, on the other hand, it represents the task itself, and so by changing the W, we change the task, and thus we change the corresponding value. Okay, so in previous work, what we did is that we train the C for a certain policy, and then for new W or new task, we are going to just compute a new value function without any retraining. All right, now in more recent works, we train a successor feature that is conditioned on three quantities. It's going to be conditioned on the state, on the action, and on a certain vector Z, which represents the tasks that we are trying to solve. So basically, this quantity is going to represent the discounted sum of future states, supposing that we start from state S and we do action A, and we follow the policy P to solve the task Z. So it's like a very rich representation of the future. So it accumulates expected discounted features under policy P and task Z. As we said, Z is going to encode the task, and the policy P can be queried for any Z without a training. The thing here is that instead of training one policy, we are going to train a conditional policy. So P can be conditioned with S and with Z as well. And by doing this, we can do like a critic recovery. So previously we did only the value recovery, but since we have the actions and we have the task vector in here, we can, with a simple dot product, so if we multiply the successor features with the task Z, we can recover the critic directly. And so once we have the critic, we can do some Bellman backups. And so we train the policy to maximize this critic. So the policy is going to try and find the best action. Yes, exactly. So generally in RL, in policy-based, in value-based methods like DDPG and TD3, we are going to have like an iterative training. So generally we train the critic, and then we train the policy to maximize the critic, and then we train the critic, like a better critic, and then we train the policy to maximize this critic, etc. Here it's going to be a little bit different. So instead of training a critic, we are going to train a successor feature. And the goal is to predict the future discounted sum of the state features instead of the future discounted sum of rewards. So basically what we replace is that instead of having R in here for the reward, we are going to be having phi of S, which is like a whole vector of features. And then we do this. And at the same time, we are going to train the policy to maximize this quantity multiplied by z. Because remember that this multiplied by this is going to recover the critic. And so we are just training P of z to maximize the critic that is conditioned on vector z. So yeah, as we said, P is learned once, and switching task Z only requires computing the critic, so this multiplied by this. Generalized policy improvement gives a policy at least as good as any single, okay? And the encoder phi of S is shared across all tasks. Exactly, because it's only dependent on the reward function itself. All right, now, as you may have noticed in here, we are supposing that we have the phi of S that is like predefined, but that's generally not the case in like most problems. So before doing all of this, before like training the successor features and the policy, we need to train the successor representations themselves. So we need to train phi of S. So how do we learn this? What we use is some basic representation learning methods. So for example, we can use autoencoders to learn relevant state features. So I guess you're familiar with autoencoders. You're going to have an encoder and a decoder. And the goal is to compress the states and try to decode it. And so we have we suppose that we have a data set of states. And for each state, we are going to pass it through the encoder. It's going to have the encoder is phi of S. And F is going to decode it back to the original format. And we try to learn a state feature that minimizes this. So that's the point of doing this. We can also use a transition model. So we try to learn an encoding phi of S that can be used with the action to predict the next state. So F here is the transition model. And the goal is to have one state feature that is very rich, that it allows us to predict the next state if we take a certain action. So as you can see, these methods are task agnostic. So we have no notion of reward so far. And so we call this task agnostic. And once we train it, we can use it with the successor features stuff. We can have more complex representations, which we call lower rank approximations. So we can have a lower rank approximation of the transition probability. So we suppose that the transition probability function can be decomposed to two matrices, so F and phi. And this is actually very similar to the transition model. So we try to learn a representation phi that is going to allow us to bridge the gap between the forward model like F of STAT and phi of S prime. So this is very similar to contrastive learning because this is a vector and this is a vector. And here we're kind of calculating the cosine similarity between the two vectors. And so what we do is that we sample STAT from dataset and we sample another state from the dataset. And if that state is not related to STAT, we want to minimize the cosine similarity because it's a whole different state. Otherwise, if S prime is equal to ST plus 1, so it's in the same transition, the goal is to maximize the cosine similarity. And so by doing this, phi of S is going to encode as rich of information as possible. A step further, we can have the lower rank approximation of successor measures themselves. So we suppose that the successor measure matrix can be decomposed to two matrices, like the F matrix and the phi matrix. And so what's different here is that in the lower rank approximation of transition probability, we are going to do some sort of Monte Carlo approximations, whereas here we are going to use some TD optimization, some temporal difference. Okay, but still they are very similar. The only difference is that instead of trying to push this cosine similarity to 0, we are going to use this instead. So instead of pushing to 0, we are going to push to the cosine similarity of F of st plus 1 with that particular state as prime. And also we have like another method that have been used in computer vision, which is called bootstrapping on latent. It's very similar to contrastive learning, except that we don't need to define like negative pairs. So from dataset, we sample a transition st80 st plus 1, and we try to learn a successor. We try to learn a state feature that is going to allow us to predict the next representation of st plus 1. SG in here means subgradient. So the idea is that if we want to learn phi of S, we have a lot of methods, and we can get inspired from any representation learning method out there. So we can use autoencoders, rendition models, contrastive learning. We can use JPA models as like shown recently. So all of this can be used to define successor features later on. So common confusions, as we said, we have like successor representations and we have successor features. So the difference is that a successor representation is kind of similar to a one-hot vector. It's only going to allow us to predict whether or not we are going to encounter a certain state, whereas the successor feature is going to be generalizable more than this. It's going to allow us to predict what are the state features that we are going to encounter. So it contains a richer information, and thus it's more useful. What's the difference between using successor features and Q-learning? So when we do Q-learning, the goal is to just predict the future rewards that we are going to collect. So it's task dependent, whereas when we use successor features, the goal is to predict the next features that we are going to encounter. And it's thus independent of any task. And that's why it's useful to do zero-shot reinforcement learning. So yes, SF stores the Psi of SA separately from W, so there is no task involved. So switching tasks only requires computing a new critic, which is just the dot product between the successor feature itself and the task vector. Another question is, does the linear reward assumption always hold? Because as we mentioned, we rely on this decomposition. So we always assume that the reward functions are going to be linear with respect to the state features. So obviously this is like an assumption that does not always hold, but when we try to train the state features, we want them to be as rich as possible, and so they must contain as much useful information as possible. And so we can tolerate this a little bit, and we can assume that the reward functions are always going to be linear with respect to the features that we learn. Now, why this is important? As we said, for example, in robotics, when we try to train an agent to solve a certain task, it takes a lot of time, and changing the task requires new training. And so we try to find like novel methods, like successor features, to train an agent independently of any task, so that once we define a task, we can directly switch without any further training, and we try to solve it. So that's the zero-shot capacity. This is also useful in multitask RL. When we have like a lot of tasks, we can't afford to train on all of them, so we train in a more general way, and then we can adapt quickly to each one of them. For navigation, so for example, we don't train agents to go to one place, for example, in a room, but rather it needs to generalize to go everywhere. And it's very inspired from neuroscience, because as humans, we do not specialize in solving one thing at a time, but rather we try to acquire like some general knowledge that can be adapted to further like solve multiple tasks afterwards. So for the end, as a summary, like as a takeaway, what you need to keep in mind is that we can't tolerate the reward decomposition. So we assume that a reward function is a linear combination of state features. And these state features, we either design it by hand or we learn it using representation learning methods. So phi of s is going to be a vector that contains the characteristics of the state independently of the task. And the w is going to be the task vector. So it's going to be a weight vector that's going to assign a weight for each characteristic of the states. And so if we have higher weights for certain characteristics, it means that this reward function favors these characteristics. And so if you try to solve it, the agent is going to try to reach states with these specific characteristics. And by changing W, we change the task, of course. We have the successor features, which is basically the expected discounted sum of future state features. And it's very similar to the critic, where it is the expected sum of the discounted rewards. So we only replace the reward function with phi of st, literally. And of course, it can transfer via generalized policy improvement or generalized policy iteration. And so to recover the value function or the critic, all we have to do is to multiply the successor features with the task vector itself. And so to have like another policy, we only need to change the W, change the task vector, and it's going to give us directly the Q function or the V function. And using these, we can have like the associated policy to it. All right, so thank you. And if you have any questions, feel free to ask them.
Thank you so much, Nazim, for this amazing talk. It was very interesting. As for me, this is the first time I get introduced to zero-shot RL. I've heard about zero-shot in different domains, computer vision, NLP, but this is the first time I see this topic. So
Yep.
Thanks a lot for sharing your knowledge. Regarding the questions, we have some in the chat so far. Starting with the first one. Is zero-shot reinforcement learning concretely implemented or still a research topic?
So far, it's very new. I can say that it's still in the research phase, but we're starting to have some concrete implementations of it. For example, there is like a tool created by Meta. It's called MetaMotivo. It's like a humanoid robot that can adapt to like new tasks, etc. So if you type in Google MetaMotivo, you're going to find it. And so you can define the task by hand or by text, and it's going to directly adapt to that. And MetaMotivo was trained using successor features exactly. More specifically, it was trained by a model that is called forward-backward, which is like a successor method for successor features. I didn't want to talk about it because I thought that was a bit too much for one session. Yeah.
Okay, thank you for your answer. Another question. Is successor features the only technique used to introduce this abstraction layer between environment and reward?
I guess it's not the only technique, but it's like the most basic one because it only assumes the decomposition of the reward function between like successor features or state features and the task vector. But we have like a lot of methods that build on top of successor features, typically forward backward. We also have TDGPA, which also builds on top of successor features, but it does things a little bit differently. So it's like the most basic way of doing zero-shot reinforcement learning, and it's the least. It's the most famous one, I guess, but it's the least competent one because the ones after are much better. Yeah.
Okay. The next question says, is there any research direction to take for zero-shot RL, like taking JPA as a backbone for the future presentations?
Yeah, exactly. So there's like a very recent paper, I think it was published in 2026. It's called TDGPA, so it's temporal difference JPA, where they try to extend the notion of successor features to JPA, and they do this exactly. They use a JPA as a backbone to learn the feature representations, and on top of these features, they just multiply it with the task vector to define the reward function. And once we have this decomposition, we can do successor features on top of this. So yes, that's like a very valid approach to do zero-shot reinforcement learning.
Yes, but is there any advantage to this approach compared to autoencoders or BEOL? Like what's very interesting about JPA when applied to RL?
All right. So when we do representation learning, the goal is to learn representations that are as rich as possible. And if you take, for example, autoencoders, the task of autoencoder is to do reconstruction. So the goal is to just decode a state and reconstruct it back. And so the kind of features that you are going to learn are only those that are important for reconstruction. But when we do reinforcement learning, we don't really care about the exact reconstruction of states. So some features that we learn through autoencoders and stuff are not that useful. The way JPA are trained, they try to predict the next state, right? And so by doing this, the representation that they learn is only relevant to predict the next state. And so it's going to kind of encode the dynamic of the environment. And so by using methods like JPA, we are going to have representations that represent the dynamic of the environment itself. And then by defining reward functions on top of these representations, we're going to end up with a much richer and a much more realistic reward functions. And by training on them, we are going to have a more generalistic agents. Yeah.
Okay. I think one last questions and it says, what are the key papers to zero-shot RL?
I've got few ones in here. I think I removed the slide. Yeah, I don't know if I can type them in here or I can just like say it like this. But there is like one very famous paper. It's called "Does Zero-Shot Reinforcement Learning Exist?" So it's a paper where they talk about successor features and forward-backward representations. So again, it's called "Does Zero-Shot Reinforcement Learning Exist?" by Ahmed Touati and Yann Olivier, I think. And it's very good paper. Another one is one representation to solve all rewards, and it's like the paper that introduced forward-backward representation. And maybe one paper that is older than this. I think it's called Universal Successor Features. I'm not sure. Exactly. It's Universal Successor Features approximations. Yeah. I don't know. I put it in chat in here. So you can take a look at these. They are very. I mean, so far for zero-shot reinforcement learning, we don't have that many papers because it's like very active area of research. So you can end up with like a maximum of 20 papers, I guess. Yeah.
Yeah. So the field is open to contribution.
Exactly. Yes. There's like a lot of room for improvement so far.
Okay. I guess this was the last question. Thank you so much, Nazim, for accepting our invitation. It's always a pleasure to have you with us.
Thank you.